Hi guys, welcome to this video. Today we're going to talk about the principles and applications of Bayes theorem in AI. The contents of today's video: the introduction, the Bayes theorem, its understanding with an example, the applications, the pros and cons, and the summary. Introduction. Probability is a measure of the likelihood of an event to occur. Many events cannot be predicted with total certainty. We can predict only the chance of an event to occur, how likely they're going to happen using it. Probability can range from 0 to 1, where 0 means the event to be an impossible one and 1 indicates a certain event. Probability means possibility. It is a branch of mathematics that deals with the occurrence of a random event. The value is expressed from 0 to 1. Probability has been introduced to predict how likely events are to happen. The meaning of probability is basically the extent to which something is likely to happen. Bayes concept. Bayes theorem, named after 18th century British mathematician Thomas Bayes, is a mathematical formula for determining conditional probability. Conditional probability is the likelihood of an outcome occurring based on a previous outcome in similar circumstances. Bayes' theorem provides a way to revise existing predictions or theories, update probabilities, given new or additional evidence. In finance, Bayes' theorem can be used to rate the risk of lending money to potential borrowers. The theorem is also called Bayes' rule or Bayes' law and is the foundation of the field of Bayesian statistics. Bayes' theorem. As you can see in the picture, which gives us Bayes' theorem, which is P slash B is equal to P slash A into P of A whole divided by PB. This is a mathematical formula for determining conditional probability. Understanding Bayes' theorem. Applications of Bayes' theorem are widespread and non-limited to the financial realm. For example, Bayes' theorem can be used to determine the accuracy of media test results by taking into consideration how likely any given person is to have a disease and the general accuracy of the test. Bayes' theorem relies on incorporating prior probability distributions in order to generate posterior probabilities. In Bayesian statistical inference, prior probability is the probability of an event occurring before new data is collected. In other words, it represents the best rational assessment of the probability of a particular outcome based on current knowledge before an experiment is performed. Posterior probability is the revised probability of an event occurring after considering the new information. Posterior probability is calculated by updating the prior probability using Bayes' theorem. In statistical inference, posterior probability is the probability of event A occurring given that event B has already occurred. Formulas for Bayes' theorem. As we know that P A slash B is equal to P and B, which is divided by PB, where PA represents the probability of A occurring, PB represents the probability of B occurring, PA slash B represents the probability of A given B, and P of P slash A represents the probability of B given A, and P of A intersection B gives us the probability of both A and B. Now let us look at an example. As a numerical example, imagine there is a drug test that is 98% accurate, meaning that 98% of the time it shows a true positive result for someone using the drug, 98% of the time it shows a true negative result for non-users of the drug. Next, assume 0.5% of people use the drug. If a person selected random test positive for the drug, the following calculation can be made to determine the probability that the person is actually user of the drug, where the terms are A, which is the probability that a positive test result is true. B, the percent of people that use the drug. A into B, the probability that a positive test result is true. 1 minus A into 1 minus B is the probability that a negative test result is true. Then the formula would look like this: A into B, which is whole divided by A into B plus 1 minus A into 1 minus B, which will give the probability of taking the drug. Using the values, the calculation works as follows: 0.98 into 0.005 whole divided by 0.98 into 0.005 plus 1 minus 0.98 into 1 minus 0.005, which gives us 0.0049 whole divided by 0.0049 plus 0.01189, which gives us the percentage of 19.76. As Bayes' theorem shows that even if a person tested positive in this scenario, there is a 19.76% chance that the person taking the drug and an 80.24% chance that they don't. Then we look at the applications of Bayes' theorem and where it is used in medical diagnosis, spam filtering, machine learning, fraud detection, legal and forensic analysis, weather forecasting, navigation, and robotics. Examples of applications. Suppose you are testing for rare disease. Bayes theorem helps in calculating the probability that the patient actually has the disease given a positive test result, considering the test sensitivity, true positive rate, and specificity, true negative rate. Naive Bayes classifiers, a type of machine learning algorithm use Bayes theorem to predict the category of data point. They are commonly used in text classification, sentiment analysis, and recommendation systems. Financial institutions use Bayes theorem to assess the likelihood of a transaction being fraudulent based on patterns observed in historical data. For instance, it can help identify unusual spending patterns that might indicate fraud. In forensic science, Bayes theorem can be used to assess the likelihood of evidence, like DNA match, given a suspect's guilt or innocence. This helps in determining the probability that the suspect is the source of the evidence. Now we look at the pros and cons. First, the pros. Bayes theorem allows for the inclusion of prior information or beliefs. This means you can combine historical data with new evidence to make more informed decisions. It updates probabilities as new evidence becomes available. This adaptive nature makes it suitable for dynamic environments where information evolves over time, applicable across various domains including finance, healthcare, engineering, and everyday decision making. Provides a consistent mathematical framework for probabilistic reasoning, helping to standardize processes in complex design making. The cons. In high-dimensional problems for which large data sets, the computations required for Bayesian updating can be complex and resource intensive. Many Bayesian models assume that evidence variables are independent given the hypothesis. In reality, variables might be correlated, affecting the accuracy of the model. The results of Bayes' theorem are sensitive to the choice of prior probabilities. If the prior is not well estimated, it can signify affect the posterior results. The effective of Bayes model depends on the likelihood models, and with the poorly specified likelihood gives indirect conclusions. Now we look at the summary. Bayes' theorem is a powerful and flexible tool for updating probabilities and making informed decisions across various fields. While it offers significant advantages such as incorporating prior knowledge and adapting to new evidence, it also has limitations including dependence on prior probabilities and computational complexity. Understanding both its strengths and limitations is crucial for effectively applying Bayes' theorem in practical scenarios. And that brings us to the end of the video. Thank you for watching.